Identify the first mechanistic step in the reaction shown below. So we see that we have an ester, and it's indicated to us that we have two equivalents of that ester and that those are coming together to form this product. So we want to hopefully recognize what this reaction is, and with an ester in this sort of reaction, this is known as a Claisen condensation reaction. And so in order to bring together two equivalents of an ester, you need to convert some of this starting ester into a nucleophile, and you need to leave some of it alone as the electrophile. And so that's what we're doing in this first step, is we're going to be converting a small amount of this ester into the enolate. So we've got sodium ethoxide. So sodium is going to be the counter ion. We're pretty used to that by this point of organic chemistry. But recognizing that what's attached to the sodium has a negative charge. And so this is the base that we're going to be using to form the enolate. So this is our base to form the enolate. And we want to notice that this base is the same as our leaving group. So we use a base that is the same as the leaving group. And that's because we know from previous chapters that esters are prone to nucleophilic acyl substitution. So if this were to attack and substitute, you're just going to be replacing one O-ethoxy or ethoxide group with another ethoxide group, and we would never be able to tell the difference. So that's why we match our base that we're using to form the enolate to the leaving group, so we don't end up with scrambling of our ester. Okay, but if this is a base to form an enolate, and this is asking us about the first mechanistic step, the first thing we need to do is form an enolate. So under basic conditions, the first thing you're going to do is deprotonate. So this is going to deprotonate at this alpha carbon. So you're going to have ethoxide. And it can remove one of those two alpha hydrogens to form the enolate. So we can draw that enolate up here. So we have a negative charge there. And so this question was just asking us about the first step. So we've actually identified the first step. So we can find that here and circle it and say the answer is C. And so we can leave it there if we want. I'm going to take the opportunity to keep going though with this mechanism and show you how we're going to form that product. So this is an equilibrium. So I'm going to draw equilibrium arrows. And it's an equilibrium that actually does not favor the formation of this enolate. You're only going to convert a small amount of the ester to the enolate, which means you're going to have a lot more of this ester available to react with that. So I'm going to draw another equivalent of the ester, and I'm just going to draw it in a different color so we can keep track of things. So we've converted only a small amount to the enolate in this equilibrium, and then it's going to react, which is going to mean we're going to pull this out of the equilibrium. So then the equilibrium will shift and form a little bit more, which can react, and the equilibrium will shift and form a little bit more, and hopefully you get the idea. All right, so what's going to happen here now is we've got a nucleophile and we've got an electrophile. So these can react with each other. And this is a key step to form a new carbon-carbon bond. So we will take a look at this. So I'm going to angle this downwards because I want to be able to show from this alpha carbon that it's bound to here. So off of this alpha carbon, I have two carbon atoms. So there's 1 and 2. Let me draw in the new bond that we formed. And then here on this carbon, we have the oxygen with the negative charge. We have a leaving group, which is the ethoxide. And then we have the 3 carbon atoms of the chain. And so what's going to happen next, this is a nucleophilic acyl substitution. So we're substituting this group for the O-ethoxide. So these electrons are going to come back down and you're going to kick off the leaving group. And so we will get to the product. if we're drawing the complete mechanism, you'd be really, really tempted to look at this and say, yep, that's the product, we're done. Unfortunately, you're not done if you're trying to draw a complete mechanism. And that's because we're in a basic solution with ethoxide. And now that we've made this 1,3-dicarbonyl, what we've made is a molecule that has a fairly acidic hydrogen. This hydrogen here has a pKa of approximately 10. And if you compare that to the pKa of ethanol, which is somewhere around 16, we've got a problem. This tells us that ethoxide is going to take off that proton. So we cannot stop this from happening. And actually, we want this to happen because every step, I just filled in these arrows, every step along the way here is an equilibrium until you get to this deprotonation step. And moreover, every step is an equilibrium that does not favor the product. So we need some step that favors the products that's going to drive this whole equilibrium forward. And that's what this deprotonation does. So we have this base, it's going to remove that acidic proton, and it's going to give us basically the anion of the product, the conjugate base, that is to say, of the product. So there's our new bond still. And now we've got the anion, okay? But we need this step to drive the reaction forward. And so overall, you have to remove one hydrogen here and another hydrogen here. So for a successful Claisen condensation, the ester that you start with needs to have 2 alpha hydrogens. So let's kind of make a note. These 2 alpha hydrogens are required. All right, and so then now we can see why we have to add the acid here in the last step, because if we don't add the acid, we're going to be sitting here at the conjugate base stage. So you need to add the acid just so you can go ahead and put that proton back on. So in terms of drawing the mechanism, it's one of those that's kind of frustrating because it feels useless. It's like you take a proton off, then you put it back on. Why are we doing that? Well, we've got to acknowledge that this is actually what happens. Whether we like drawing these extra steps or not, this is actually how the reaction goes. All right.